We also briefly discussed this example. So in this example, the cache size is given 1024 words, okay, and the block size, the size of the block in each cache location is 1 word. So first of all, how do you determine the total number of blocks in a cache? What you do is total number of data, total number of words in the cache divided by the total number of blocks. Here in this example, it is only block size. So here it is only 1. Okay, so the total number of blocks in a cache is 1024. So if you were to represent that 1024 value in the power of 2, it will be 2 to the power 10. So we need 10 bits to address each individual block in a cache. Okay, as same as we needed 3 bits to address 8 blocks in a cache. Similarly, we need 10 bits here to address each 1024 block in a cache. Understand? So here, when this 32-bit address, the 10 bits are index field. Okay, so when the data is requested, processor try to match this index field with the for example, first of all, the processor will locate this block indicated by this 10 bits field in the cache. Okay, so whatever the value of this 10 bits field, it will find that particular block, and then it will determine if the data present in that particular block is the data that being requested. How it is matched? It matches with the tag field. So upper 20 bits are matched with the 20 tag fields here. If they are both matched, it means that the data that is requested is found in the cache. And if it is valid data, then we call it a hit, and the data that is being requested is produced, 32 bits data. Okay. So let's look at the actual tag bit size here. In this previous example, we had a 32-bit address. Cache size is represented in the power of 2 to the power n blocks. So n bits are used for indexing. Block size is 2 to the power m words. So there are 2 to the power m plus 2 bytes in a block. So if you were to look at the previous example here, what is the block size? It's 1 word. How do you represent this in the power of 2? 2 to the power 0 is 1 word, and there are total 4 bytes. So 0 plus 2 means 4 bytes in each word. Okay. So m represents word number, n represents index field, and value 2 is the byte part of the address. So with the help of this formula, we can determine the size of the tag field. Okay. So what would be the total number of bits if you were asked to calculate the total number of bits including the valid bit in a cache? So this would be the general formula. So first of all, look at this field, which is the same. This is the tag field. So here again, what we are trying to do is to determine this thing, the size of the total number of bits in a cache. Okay. So let's try determining for the first one. This is the tag bits. This is 1 valid bit with each block. This is the data bits in a block. So if it is 2 to the power m, 2 to the power 0, which means 1 word, so every word has 32 bits. Okay, so total number of bits in a block, and there are total 2 to the power n blocks. So this will give us the total number of bits in a cache. So this is how you should be calculating total number of bits in a cache. So if you solve this part, it will become this, and this is actually the address field. So if the address is 32-bit, you will put 31 in this formula. Okay, so if the address is 64-bit, you will put 63 here. Okay, 1 value less than the actual address field. Understand?
Can you explain the cache size in a table?
The cache size is 2 to the power n number of blocks. So in the previous example, there were 1024 blocks here. The cache, the total number of blocks is 1024. So 2 to the power 10 is the total number of blocks in a cache. Okay, so this 10 represents the value n. We represent it with the value n.